This chapter is Spectroscopy B, and we'll be looking at infrared spectroscopy. And it turns out infrared spectroscopy is an incredibly useful tool in organic chemistry. We'll start by looking at electromagnetic radiation. Infrared radiation is part of the electromagnetic spectrum. So we'll find that all electromagnetic radiation travels at the speed of light, which is about 3.00 times 10 to the 8th meters per second. The actual number, if you look on the periodic table that is available on the website, you'll see here we've got the speed of light, and that is the exact value by definition is 2.9979248 times 10 to the 8. For most calculations, we can round that to 3.00, just depending on how accurate we need the measurements. This will do for most things. So we'll find that the speed of light is equal to the wavelength times the frequency. So c, which is that speed of light, is equal to the wavelength of the light times the frequency of the light. And the frequency is measured in cycles per second or waves per second. Sometimes that is called hertz. So if you see Hz, that is the same thing as reciprocal seconds. Here, these are some common units that are used for wavelength when we're talking about wavelength of light. And so these common units, meters, you might use for if you're talking about certain types of radio waves, you might use meters, centimeters for like microwaves. And then you get into micrometers, that's going to be in the range of infrared, nanometers for, from anywhere from X-ray, UV, and visible light. We typically use nanometers. And sometimes you'll see angstroms used as a unit of measure. So, as you probably know from previous classes, electromagnetic radiation comes in smallest units, and those smallest units are photons, and the energy of those individual photons is proportional to its frequency. So E equals h nu. And then h is Planck's constant, and it is a universal constant. And if we go back to that periodic table I was showing you a minute ago, it's right there next to the speed of light. So we want to briefly look at the electromagnetic spectrum and see where infrared falls into this gap. So it is arbitrarily divided into different sections. We divide it this way mostly based on how we observe it and some of the characteristics of it, but it is somewhat arbitrary how we do this. So there's the visible part of the spectrum, which we are familiar with, ranging from 400 nanometers to 750 nanometers. The ultraviolet, anything to the left over here, is going to be higher energy and higher frequency and shorter wavelength. All of these things, ultraviolet, X-ray, and gamma radiation, those are all what we refer to as ionizing radiation. And these are the ones that tend to be more hazardous than things over here. And so ultraviolet, we will look a little bit at ultraviolet in the chapter on conjugation coming up here in a few chapters. And gamma radiation, that's mostly used with nuclear kinds of processes. So, and then X-ray radiation is not something we're going to talk about much in this class, but it is an important part. Let's get over to the infrared. And the infrared part of the spectrum, the frequencies here correspond to the frequencies that bonds in molecules vibrate back and forth and bend and stretch. And so it turns out that it's really, really useful for looking at the types of bonds that you have in your molecule. And so that's what we're going to be looking at. Microwave, there's not anything that we'll be talking about in this class that's microwave, but in the next chapter where we talk about NMR, we will be looking at radio waves and how radio waves interact. Very, very low energy things. So again, looking at this spectrum, as the spectrum goes further to the left, we're getting to shorter wavelength, higher frequency, and higher energy photons. All right, so putting it all together, what the relationship here is that the frequency and the wavelength are inversely proportional. So the frequency is equal to c over lambda. So that is our formula for that. And then the energy is going to be equal to, so we know that E is equal to h nu. Well, that means we can also get that, let's see, yes, so E is equal to h nu. That means we can also get that hc over lambda is equal to the energy. So wavelength is inversely proportional to the frequency, and it's also inversely proportional to the energy. And that makes sense because frequency and energy are proportional. So the energy of a photon will increase as its frequency increases. And the energy of a photon will decrease as the wavelength increases. So we're going to look just ever so briefly here. I'm going to jot down these equations. We're not actually going to calculate, but I'm going to put the E equals h nu, and that is equal to hc over lambda, and then nu is equal to c over lambda. And the reason I want to do that is so we can refer to it when we are looking at these problems. All right, so which of the following has the higher frequency? And so since the things here are given in wavelength, and wavelength is inversely proportional to frequency, the shorter the wavelength, the higher the frequency. So if we look here, the wavelength, we have 10 to the 2 and 10 to the 4 nanometers. Well, 10 to the 2 is a shorter wavelength, so this will have a higher frequency. All right. Since wavelength is also proportional to the energy, then that means it also will have higher energy. All right, so that one. All right, light having a wavelength of 100 nanometers or 100 micrometers. Here we just have to know which one's shorter, and the 100 nanometers will have the higher frequency and the higher energy. All right, I'll just put both those there. All right, and then red light or blue light. You may or may not remember this from that previous page, but I'm going to go back. All right, and blue has a shorter wavelength than red light. And since blue has a shorter wavelength, that means it has a higher frequency and a higher energy. So we'll go back over here. The blue light, again, and I'm just going to point it to that same thing, higher frequency and energy. All right, so let's return to this page, and we'll go to the next thing. All right, we did this already. All right, so we want to look at energy changes in molecules. What's happening when a photon is absorbed by a molecule? So when any kind of electromagnetic radiation comes in the vicinity of a molecule, and I say here it strikes a molecule, but if it interacts with the molecule, we'll find that some wavelengths of light are going to be absorbed, but not all of the wavelengths are absorbed. In order for absorption to occur, the energy of the photon needs to match the difference in energy between two different energy states of the molecule. So, so for infrared, like if we have a molecule that is in one vibrational state and we have a photon that matches the difference between that vibrational state and another vibrational state, then it can absorb a photon at that range. And so what we need to do is we need to understand what kinds of things affect this change in energy or change in frequency, because we know frequency is related to this. We'll find that the larger the energy difference is between the two states, the higher that energy of the radiation is needed for the absorption. For these infrared energy state differences that we're going to be looking at, these are energy differences, again, in vibrational states of the molecule. When we look at, a little bit later, when we look at ultraviolet, we're going to be looking at differences in energy between a ground state electron and an excited state electron. And so that's a whole different thing. It's talking about the electronic states instead of the vibrational states. But anytime electromagnetic radiation interacts with matter, this is what's happening. If it gets absorbed, it's because it matches up to one of these energy state differences. So let's look at what is actually happening with the molecules. So if we absorb an infrared radiation, that will cause the vibrational changes to the molecule. And the types of vibrations that we're going to be looking at are stretching vibrations and bending vibrations. And there's some complex bending vibrations that we won't really get into. We're mostly going to be interested in the stretching frequencies of these molecules. All right. These vibrational modes are quantized. So it could have one vibrational state where it is vibrating back and forth at a certain frequency, and then when it gets hit with the right frequency of infrared radiation, the right energy, it can cause that molecule to jump up to a higher energy state. And when it does, it will be vibrating with a greater amplitude. So when that IR matches up, the energy of the infrared photon matches up to the difference in energy between the vibrational states, we can cause the molecule to vibrate at a higher amplitude. And this is the basis of infrared spectroscopy, is that we shine the infrared radiation through a sample, and some of that infrared radiation is going to be absorbed because of these differences in vibrational states. So let's look at an actual infrared spectrum, an IR spectrum, as we like to say for short. All right, so in an infrared spectrometer, the light will pass through the sample, and frequencies that match frequencies of the vibrational frequencies are going to be absorbed. And the remaining light is going to be transmitted through the instrument all the way to the detector. And you'll notice I say sort of, there's some hand waving I'm doing here. It gets a little bit more complicated. Here is an example molecule, and this one is I think it's butanol, but it's an alcohol for sure. And you'll see that there's different kinds of peaks here. We have this big broad peak, which by the end of this chapter, you will know that a big broad peak like this is an OH peak that you would see in an alcohol. And then a peak like this that is to the right of 3000, you'll know that that is a carbon-hydrogen stretching. Again, I'll go over those here briefly. Now, there's two different ways that we can number the graph. And those two different ways kind of depend on, what context you're using. But for most organic chemists, we will use what seems like an odd number, or what seems like an odd kind of calculation, but it's actually pretty useful because it gets it to numbers that we can remember, and that's called the wave number. The wave number is simply the wavelength it's the reciprocal of the wavelength. And if you put that wavelength in centimeters, then you will get the wave number. So, and then on the y-axis, we have the percent transmittance. If all the light goes through, that's 100% transmittance. So you can see this sample is not absorbing anything right here, hardly anything there. But here, where there is an absorbance, we've got a fairly low transmittance. So this molecule is absorbing a lot of that particular frequency. So the weird thing about the wave number is we use the symbol that we use for frequency, but we put a little mark above it. And so this symbol, the reason that we use the same one for frequency, even though it's not the frequency, is that it's proportional to the frequency. If you double the wave number, you double the frequency. You also end up doubling the energy. So, this is a useful way of thinking about it. So 1 over the wavelength is equal to that. So if you take whatever the wavelength is, put it in centimeters, and then take 1 over, you will get these numbers. Now, if you want, you can have just straight up wavelength. These are in micrometers. And so if you take these numbers, the micrometers, and let's see, to get it to centimeters, you would have to multiply by 10 to the 4, and then take, you would have to divide by 10 to the 4, and then if you take the reciprocal of that number, you'll get these numbers down here. You can give that a shot, and well, actually, here, I'm going to show you, just so you believe me, so you don't think I'm making this up. All right, so I'm going to very briefly go back over here. Let's take that where it says 5 up here. So that's 5 micrometers. So we'll take 5, and we're going to divide that by 10,000. All right, and then we're going to raise that value to the -1, and we're going to get 2,000. So if we go back over here, you'll see that 5 lines up with 2,000. So that's how those are related, in case you're curious. All right, most of the bonds that we're interested in are going to have absorptions in the range from 4,000 reciprocal centimeters to 400 reciprocal centimeters. And you can see here, that's the 4,000, and this one only goes down to about 700 there, but you could go a little bit further. We'll talk about what these different peaks mean and how we use them here in just a bit. So let's go, move that calculator out of the way. Let's go back over to this. So here we've got wave numbers. We've got IR radiation, IR light, with a wave number of 3,000 reciprocal centimeters or 1,500 reciprocal centimeters. Well, remember, wave number is proportional to the frequency, which is also proportional to the energy. So the larger the wave number, the higher the energy. So that one is higher energy. Now this other one here, we've got 10 micrometers and 20 micrometers. Those are also in the infrared part of the spectrum. Only the 10 was on the page I showed you a minute ago, the spectrum that I showed you a minute ago. The 20 doesn't quite match up there, but for purposes of this, we can these are both in the infrared part of the spectrum. Remember that energy is inversely proportional to the wavelength. So the shorter the wavelength, the higher the energy. So this one will be higher energy. All right, so that's pretty straightforward. Well, let's go back and look at the next thing. So now we want to talk about the different regions in the infrared spectrum. So where are the different regions? there's two regions that we will distinguish. One, we're going to refer to the functional group region, which is where we have wavelength or wave numbers that are greater than 1500 reciprocal centimeters, and the fingerprint region, which is less than 1500 reciprocal centimeters. So greater than is going to be over here on the left, and you'll notice there's not a whole lot there. There's a peak there and a group of peaks here. We'll find that in this region, functional groups are relatively easy to identify. So IR is a very powerful tool for identifying those functional groups. Over to the right of it, which is less than 1500 reciprocal centimeters, we'll find that this is in what we call the fingerprint region. It's still different vibrations and stretching and bending motions of the molecule, but there are a lot of very subtle interactions that go on. And so the reason they call it the fingerprint region is often this part is unique for different molecules. Now, if you have two molecules that are almost identical in structure, it's difficult to see a whole lot of difference in there. But if you use a computer, you might be able to distinguish those if you have like a database of these fingerprint regions. We're going to stick primarily to the functional group region from 4,000 to 1,500 reciprocal centimeters. That's going to give us the most benefit for a relatively small amount of memorization and learning. All right. And then again, I'll point out these peaks right here, the carbon hydrogen and then this carbonyl. These peaks correspond to the stretching frequencies of the carbon oxygen for the carbonyl and the carbon hydrogen that are all over that particular molecule. Over here, we also have a carbon hydrogen and a carbonyl. And you'll see that on the functional group side, these two spectra look very similar. What's different is over here in the fingerprint region. There is a pretty big peak here that's at about 1200, and that 1200 matches up to the stretching frequency of this carbon-oxygen bond. But often that peak is surrounded by a bunch of other peaks that are kind of hard to distinguish. So, all right. We can think of bonds as springs that have weights on the end. It's not a perfect analogy, but it's actually pretty good. And so the behavior of springs is governed by Hooke's law. And so here is Hooke's law. It says that the wave number is going to be equal to a constant. We're not going to worry about what the constant is at this moment because we're not going to actually calculate these things, times the square root of this ratio of a force constant over the mass. Well, that force constant is essentially the strength of the bond. All right, and then the mass is the mass of the atoms that are on that bond. So the strength constant, which is the strength of the spring, is analogous to the bond strength of the molecule, and the mass of the weights is going to be analogous to the atomic mass. If you have two springs with the same weight on each end, the stronger spring vibrates at a higher frequency. So, if you've got two different carbon-hydrogen bonds, and we're going to see this here in a minute, carbon-hydrogen bonds that are a little bit stronger are going to vibrate at a higher frequency. If you have two springs of the same strength, springs with lighter weights will vibrate at higher frequencies. So we'll find if you've got a carbon oxygen bond versus a carbon nitrogen bond, the carbon nitrogen bond will vibrate at a slightly higher frequency than the carbon oxygen bond, provided that the bonds are the same strength. All right, so let's look at the regions of the infrared spectrum we're going to break down the functional group region into 3 sections. Again, the fingerprint region mostly gives us single bonds, but because there are so many single bonds and we get some bending interactions over here, we don't typically try to identify these. But for double bonds, triple bonds, carbon-hydrogen bonds, oxygen-hydrogen bonds, and nitrogen-hydrogen bonds, these things are very easy to identify in the infrared spectrum, and so we will be able to find those just by looking at some examples. All right, so here is a list of important infrared absorptions that I want you to memorize. I don't often say, hey, memorize all this stuff. For this, yes, I want you to memorize it. It's not too terribly bad. There's just a limited number of things that you will have to memorize. And if it's any comfort, and I'm sure this will be no comfort at all, this is smaller than the list of ones I had to memorize because they wanted me to memorize the single bonds too, the ones that were in the fingerprint region. But these are the ones that I want you to memorize. So the OH, we saw one of those a few minutes ago with that alcohol, and it had a wave numbers from 36 to 3200 reciprocal centimeters. That one's very broad and very smooth for an alcohol. For NH, it's not quite as broad and not quite as prominent as the OH bond. The reason that these are so spread out often is because of hydrogen bonding. It causes them to have many different frequencies that they vibrate at. Something really cool happens with carbon-hydrogen bonds. sp3 hybridized carbons bonded to a hydrogen, those are going to have wave numbers from 3000 to 2850 reciprocal centimeters. sp2 hybridized carbons, they're a little bit shorter and a little bit stronger, and because they're stronger, they're going to vibrate at a higher frequency and therefore higher wave number. And so you'll see those from about 3150 to 3000. And since these don't really overlap, that means you can clearly identify when you have carbon hydrogen that's sp3 and carbon hydrogen that's sp2. Carbons that are sp hybridized with a hydrogen on them, like an alkyne for example, they have a stretching frequency at about 3300, and these tend to be a little bit narrower and not quite as strong as the ones that are sp2 and sp3, but these are definitely distinct. So, all right, you kind of get into an interesting sort of no man's land with triple bonds. Right at about 2200 to 2300, you'll find the triple bonds and carbon dioxide. The triple bonds they're very short. For carbon-carbon triple bond and a carbon-nitrogen triple bond, they're very short, and they have these both have an absorbance very close to 2250. It can often be difficult to distinguish between these two, so if you have both of these in a particular functional or a particular molecule, they may overlap. Carbonyls are very distinctive because they're very strong absorptions. They often look very characteristic, and they range from about 1800 to 1650, often close to 1700. And a little bit later, we'll be able to tell the difference between something like an amide and a ketone based on these absorptions, which is very, very convenient. All right, and then here we've got carbon-carbon double bonds. They have a moderate absorption at about 1650. And then phenyl, when you have a benzene ring present in the molecule, it's going to have two absorptions, one at about 1600 and one at about 1500. And it won't be perfectly those numbers, but it will be pretty close. So that's pretty characteristic. If we go any further, we're getting into the fingerprint region, and we're not going to be focusing on those. All right, so let's look at bond strength and percent S character. I mentioned this a minute ago. These are very subtle differences, but the more S character you have, so sp3 versus sp2 versus sp. sp3 has 25% S character. These tend to be longer bonds and not quite as strong as the carbon hydrogens that are on sp2. They have 33% S character. And the carbon hydrogens that are on sp have even more S character. They're 50% S character for those carbons. So those are even shorter bonds. The shorter the bonds are, the stronger they are, and the higher the frequency. And as we saw in the chart, from 3,000 down to 2,850 for sp3 hybridized carbon hydrogens, 3,150 to 3,000 for sp2 hybridized carbon hydrogen bonds, and then finally for about 3,300 reciprocal centimeters for sp hybridized carbon hydrogen bonds. So let's look at number 21 and 22 on the in-class assignment. So I'll switch over. All right, and we want to know, how will these differ? What's going to be different about these? Well, first of all, one thing I like to point out is what's going to be the same. All right, so I'll put the same over here. So what do they have in common? Well, both of these have carbon sp3 hydrogen bonds. And so we should expect both of them to have absorptions from 3,000 to 2,850 reciprocal centimeters. Okay. Now, how are they different? Well, this one has a carbon-carbon double bond. And if you go back and look at that chart, you'll see that it has an absorption at about 1,650 reciprocal centimeters. And then we also have a carbon sp2 hydrogen, which will be from 3,150 to 3,000 reciprocal centimeters. This one will have a carbon-carbon triple bond, and it has a pretty unique absorption at about 2,250 reciprocal centimeters. And we'll also have a carbon sp hydrogen, and that one also very characteristic at approximately 3,300 reciprocal centimeters. So if you put these two compounds, which are isomers of each other, if you put these two compounds into the infrared, you should very clearly be able to tell which one is which. And you know, these will be the same, but this will be different than that. All right, let's do the same thing with part B. So on part B, we've got, well, again, let's look at what's the same. So the same for both of these, they're both going to have a carbon-oxygen double bond, which is at about 1,700 reciprocal centimeters. And they will both have carbon sp3 hydrogens, right? Because there's a methyl and ethyl, all right? And those are going to be, again, at 3,000 to 2,850 reciprocal centimeters. Okay, now let's look at what is different. Well, there's really one big difference that's going to happen here because you know, this has the what do you call it? It has the OH. All right, and the OH on a carboxylic acid is actually a little bit broader. I'm going to show you an example of that one a little bit later, but it's from about 3,600 all the way down to about 3,000 reciprocal centimeters. And this has no OH. So we should be able to tell these apart very easily. And that's going to be the biggest difference between these in the functional group region. All right. For this one, things that are going to be the same. Definitely carbon. Again, I'll put same here. carbon sp3 hydrogen from 3000 to 2850. All right. And then that's it as far as what's going to be the same. As far as what's going to be different, well, this one will have a carbonyl stretch at about 1700. And this one will have no carbonyl stretch. And that will be the easiest way to distinguish between those. This one has a carbonyl, this one doesn't. All right, so now what's going to be saying? I'm going to put, instead of same, I'm going to put similar on this one. So the carbon triple bond is at about 2250. And the carbon nitrogen triple bond is also at about 2250. Since those are so close to each other, you may not be able to distinguish between those two. All right, and then as far as what's the same, they both have carbon sp3 hydrogens, which again 3000 to 2850. All right, and that's it. Now, looking at what should be different. Well, this should have a very distinctive peak. That's carbon sp hydrogen, and it's at about 300 centimeters, reciprocal centimeters, and this one won't. So this one has no carbon sp hydrogen stretching. So you'll see this one at 3300 because it has that terminal alkyne, and then this one we won't get that peak. So there's a lot that's going to be similar, and this will be the main difference between those two. As one will have that and the other one won't. All right, let's look at 22. We've got some drugs on here that you certainly have heard of. So morphine, heroin, and oxycodone. Morphine is naturally occurring. It's extracted from poppies. Heroin is a derivative of morphine. They found that when people got addicted to morphine, so they were trying to make it less addictive. So they took it and put these acetyl groups on there, and it turns out that didn't work at all. It made it even more addictive. So heroin is that. It also makes it a little bit more potent. And then oxycodone is a derivative. You'll see that if you, like, a double bond here is changed, and here we've got an OH that is on this bridgehead. So there's a couple of little subtle differences. This, instead of an OH, has an ether linkage, and here, instead of having an OH, it's got a carbonyl. So there are some things that are different. We want to be able to distinguish these using just the IR. So I'm not going to list all the things that are the same because there's a lot of similarities. They all have a phenyl group. They all have carbon-nitrogen bonds. None of them have nitrogen-hydrogen. So this one will have an OH peak. And again, that's at 3600 to 3200. All right. And it'll have no carbonyl. This one will have a carbonyl at about 1700, but no OH. All right. And this one will have a carbonyl again at about 1700, but it also will have an OH at the 3600 to 3200. So we should be able to very quickly, if we took quick spectra of these, we should be able to distinguish between morphine, which has the OH but no carbonyl, heroin, which has the carbonyl but no OH, and oxycodone, which has both a carbonyl and an OH. All right. All right, let me say something quickly about symmetry. There are certain types of bonds that will not absorb in the infrared spectrum, and I will show you an example of that. In order for a bond to absorb, there must be a change in the dipole moment during the vibration. So that means it has to have at least some dipole moment to begin with, and that as it vibrates back and forth, that dipole will change. If you don't have that change in dipole, that infrared radiation will not absorb. It just that's just the nature of it. So if we have perfectly symmetrical nonpolar bonds that don't have a dipole, all right, then they will not absorb in the infrared. They are infrared inactive. And an example of this is 2-butene. So here in the, or I guess we should call it but-2-ine, but so 2-butene here, it's got this carbon-carbon double bond. It is a nonpolar, or triple bond. It is a nonpolar bond, completely nonpolar. So there's no dipole, and when it stretches, there's still no dipole. So that means that it is not reactive. Other things that are not IR inactive are going to include, like in our atmosphere, oxygen, which makes up about 79% of the atmosphere. Nitrogen makes up about 78%. Oxygen, which makes up about 21%. Those two things are IR inactive. Now, ozone is IR active because it's a little bit polar, but the regular oxygen and nitrogen don't absorb in the infrared. That means 99, well, if we throw in another percent for argon doesn't even have any bonds, so it's IR inactive as well. That means most of the atmosphere does not absorb infrared radiation. Almost all of that infrared radiation is absorbed by water, carbon dioxide, and some other trace elements that or trace compounds that get up into the atmosphere. So kind of interesting. All right, so in this section, we're going to be looking at a bunch of different IR spectra and seeing what we should expect. They're labeled, so it's not too terribly difficult. Hexane is a very simple compound. We've got carbon-carbon bonds. Those carbon-carbon bonds are going to show up over here. That's what these very simple peaks are. And we've got carbon-hydrogen sp3. So you'll notice that it's to the right of 3000. So this is from 3000 to 2850 is where those peaks are. And that's it. There's no carbonyls, there's no OH, there's no other polar bonds. So we're just not going to get it. So we'll have the 3000, 2850, and then there's some carbon-carbon single bonds that we don't even have on this chart. But that's what those other things are in the fingerprint region. All right. Let's mix it up a little bit, and we'll put hexene, hex-1-ene. All right, well, we still have the carbon-hydrogen sp3 that is from 3000 to 2850. We've got a carbon-carbon double bond. You'll notice that it's very sharp, but not super strong. But we've got that carbon-carbon double bond there. Again, this is all stuff over in the fingerprint. And then here we've got a carbon sp2, hybridized carbon, hydrogen. And you'll notice it falls in that range from 3150 to 3000. It's separate from this. And so that is a good way to determine if you've got double bonds. You look for the peaks over here, and then you look for carbon sp2 hybridized bonded to hydrogen in that 3150 to 3000 range, and that is a giveaway that you've got double bonds. All right, here for a triple bond, again, there's stuff over here in the fingerprint region, but what's really cool is we've got that carbon-carbon triple bond, which is a very distinctive peak in a sort of out where not much else shows up, is at 2250, give or take a little bit. All right, we've got the sp3 hybridized carbon hydrogen. Let me go ahead and pull the table up. And then we've got this terminal. It's a terminal alkyne. So it has a carbon sp hybridized bonded to a hydrogen. And that's what gives us that peak that's at about 3300 and right there. So very unique spectrum. So you should be able to identify a terminal alkyne, and you should be able to distinguish between a terminal alkyne and an internal alkyne. All right, here is butanol. I don't know if this is exactly the same one we saw earlier, but this is a 2-butanol. It's an alcohol. And the most prominent peak is that OH. And you'll notice it goes all the way from 3,600 to about 3,200, even a little bit further. But that is the OH stretching frequency. It's very broad and it's very smooth for an alcohol. So we'll find that all alcohols will look like this, is that they'll have that smooth, they'll have that very smooth and broad peak. So if you see that, almost certainly it's an alcohol. I will caution you that if you have a sample and it's possible for it to absorb a little bit of water, you might see the same thing coming from water if you have a lot of water in your sample. So word of caution there. All right, and then the carbon hydrogen, it's not labeled here, but the carbon hydrogen, since these are sp3 hybridized carbons, it's from 3,000 to 2,850. So you're getting used to seeing those. And then everything else falls in our fingerprint region. All right, now this one was not in the chapter. It's later in the textbook, but I purposely put it here. This is butanoic acid. And I want you to look at the differences here between the OH stretching frequency for butanoic acid. It's still fairly smooth, and it's very broad, and it extends from about 3,600 all the way down to below 3,000, and it often will obscure the carbon hydrogen. So like you'll have two peaks on top of each other here that do this. And then here is the carbonyl that's associated with the carboxylic acid. So you should be able to, by looking at the shape of that OH and the extent of it, you should be able to distinguish between an alcohol and a carboxylic acid just by looking at the OH, which that's a pretty cool tool, pretty powerful to be able to do that. All right, here is butan 2-one or 2-butanone, if you want to call it that. All right. Again, the most prominent peak here is the carbonyl, which is at about 1,700. But then we also have the carbon hydrogen, the sp3 hybridized carbon, which is 3,000 to 2,850. Very characteristic. We don't have any that's going over into that 3,150 to 3,000 range. So no sp2 here. And then this is either an impurity or some sort of artifact. It could be an overtone. I'm not sure. All right, so carbonyl and carbon hydrogen. All right, here is diethyl ether. And with the diethyl ether in the functional group range, there's really only one thing that is showing up here, and that is the carbon hydrogen stretching. Now you'll notice this fairly prominent peak here at about 1,100. That comes from the carbon oxygen stretching, but again, you don't have to know that. It's just kind of interesting if you're wondering what that is. But you'll notice no carbonyl, no OH, just diethyl ether. All right, here is octylamine, and a couple of interesting things happen here. We get an NH peak. Notice that the NH looks very different than the OH. The OH is very, very broad and very strong, and the NH is much less broad and much less of a intense signal. So the double peak here comes because there are two hydrogens, and it turns out that there are two modes of stretching. There is symmetric stretching and asymmetric stretching. We'll talk about that later. If you had an isomer of this that was that was a secondary amine, so we had an alkyl group instead of two hydrogens here, we had an extra alkyl, we would only see one peak there. But of course we do see the carbon hydrogen stretching here for all the sp3 hybridized carbons. All right. All right, here is a nitrile, and we've got that very characteristic peak for the nitrile that's at about 2250. So here we go. There's the 2250 for the carbon nitrogen. So only our triple bonds show up here. These are some other bonds, some carbon-carbon bonds and stuff. And then here we've got all these carbon hydrogens that are fairly easy to identify. So let's look at number 18. Switch over to 18 here. All right, so what are the major IR absorptions? All right, and so we just want to identify which ones are going to be the prominent ones in the functional group region. We don't want to worry about fingerprint. All right, this one, there's only one that we're really interested in, and that's carbon, sp3 hydrogen. And at this point, you probably have memorized this from 3,000 to 2,850 reciprocal centimeters. All right, so here we've got cyclohexanol. The most prominent peak is going to be that OH peak, and now you know what that looks like. So 3,600 to 3,200. And then the carbon sp3 hydrogen is going to be the 3,000 to 2,850. All right. This one has the two most prominent things are going to be related to the double bond, but let's go ahead and put everything in there. So we've got carbon sp3 hydrogen. And that one again is 3,000 to 2,850. All right, we've got carbon sp2 hydrogen because there's hydrogens here and here. And those are going to be 3,150 to 3,000. All right, and then we've got that carbon-carbon double bond that's going to show up at about 1,650 centimeters. All right, here we've got cyclohexanone, and there is an experiment where we take cyclohexanol that we do in lab, where we take cyclohexanol and convert it into cyclohexanone, and IR is one of the ways we determine if we've done that experiment correctly. So here again, it is going to have the sp3 hybridized carbon, and it'll be 3,000, 2,850. And then that carbonyl should be very distinctive at about 1,700 reciprocal centimeters. It should be pretty strong. All right, so for this next one, we've got oleic acid. There's multiple things here to pay attention to. Let's go ahead and get the most prominent thing, the OH, which is for the carboxylic acid. And as you recall, it is much, much broader. It's much, much broader than regular alcohol OHs. So our OH for our carboxylic acid is going to be 3,600 down to 3,000-ish, but it may even go further than that. So, but it is much broader than the alcohol. We'll have the carbonyl. It's going to be at about 1,700. All right. We've got carbon sp3 hydrogens. And again, those are 3,000 to 2,850. We've got carbon sp2 hydrogens, right? So right there and there. And those are 3,150 to 3,000. All right, so we should have peaks on both sides of 3,000 there. And then we've got one more, that carbon-carbon double bond. And it usually comes in at about 1,650, give or take. All right, this one, there's a lot going on here. So there's just, we'll just go through the list. I would say the most distinctive peak in this is probably going to be the carbonyl, but let's just kind of work our way through. We'll start with the OH. So the OH will be 3600 to about 3200. All right. We'll do the phenyl group. And there's multiple things that are going on. That's why we get a double peak. But we get one that is at about 1600, and one that is at about 1500 reciprocal centimeters. So there's two peaks that are involved for the phenyl. All right, let's look at the NH. And that one usually is a little bit narrower than the OH. And so usually it's at about 3,500 to 3,200. And it should be a single peak because we've got a secondary amide here. All right, we got the carbon oxygen, which again is at approximately 1,700 reciprocal centimeters. All right, and then we haven't even done the carbon hydrogen, so carbon sp3 hydrogen, which should be 3,000 to 2,850. Carbon sp2 hydrogen from 3,150 to 3,000. And then for the last thing, we've got this carbon-carbon double bond at about 1,650 reciprocal centimeters. So let's look at our next section, which is talking about infrared spectroscopy and structure determination. We can get a lot of information about what functional groups are present using infrared. And so this has been an extremely powerful tool for chemists over the last 100 years. And one example is in the 1940s, after penicillin had been discovered, and they were trying to figure out what exactly the structure of penicillin G was. They had two proposed structures, one that was this structure, which is the correct structure, and one that was this. You'll notice this one has what's called a beta-lactam, and this one has it does not have a lactam in there at all, and it's definitely doesn't have that 5-membered ring. Turns out that, and we'll talk about this later in a later chapter, when you have carbonyls that are in a strained ring like this, those carbonyls end up having a higher frequency, and so they'll have a higher absorption. So the carbonyls on the beta-lactam are about 1760, that's higher than you get for most amides. And so they were able to rule this structure out and determine that it was this, that's kind of cool. So that was one of many things that they were able to determine doing this. And you can use this, you can use similar kinds of things, but most often when we're using this in organic chemistry, we're using it to determine what functional group is present. And if we can determine what functional group is present, we can rule out a whole bunch of other possibilities. So here is an experiment that's similar to one that we do in class. You can use this to determine the outcome of a chemical reaction, determine did the reaction occur. And so here, if we take an alcohol and we oxidize it to a carbonyl, and so like we can use a chromium-6, it'll oxidize it. We can end up with a carbonyl. The OH has a very distinctive absorption out in the 36 to 3200. whereas the carbonyl doesn't, and it's got an absorption at about 1700. So very different. We do something very similar in our labs for one of our experiments. All right. And then finally, we're going to look at what happens when we combine the power of infrared and mass spectrometry. And what it allows us to do is that we can determine, or at least get a pretty good idea of what a structure is by looking at the molecular ion. Sometimes we can get information about functional groups if we look at fragmentation patterns, although we're mostly going to look at molecular ion. And then we can look at the information in the IR to tell us what kind of functional groups are present. So I want you to look at this. This has carbon, hydrogen, and oxygen. I want you to look at this IR, and based on what we've talked about, what kinds of functional groups are present. So pause the video and see if you can figure out what functional groups are present. And mostly it's those two peaks here and here. All right. So now that you've had a chance to think about this, when you look at this, you'll see, all right, these are to the right of 3000, which tells us these are all sp3 hybridized carbons bonded to hydrogens. So all of those bonds there. And that here we've got a very distinctive carbonyl structure. So from that, can we get information about what this is? 88. Well, let's break down the 88 because that's our molecular ion. You can see the 1% peak there. If it's 88, that gives us a little bit of information about what it is. And there are several possibilities here. If we just do 88 divided by 12, that means we could have what, 7 possibilities, right? If 7 times 12 comes out to 84 with 4, so that gives us 4 left over. So there's the remainder. So the structure could be C7H4. Well, that's not very likely because we know it has oxygen in it. So if you take one carbon away and then add an oxygen, you could have C6O. Well, that seems unlikely too because that we need a carbonyl. We didn't have other carbon-carbon bonds. We have carbon hydrogen, so we need to have some hydrogens in there. So if you take one more carbon away and add some hydrogens, we get C5H12O. All right, well, C5H12O is a good possibility. However, you'll notice that that is a saturated hydrocarbon. If you go through and look at the degree of unsaturation, like we did in Chapter 10, then you can determine that the degree of unsaturation here is 0. The degree of unsaturation for this is 1. And the degree of unsaturation for this one is, let's see, 3 times 2, 6 plus 2 is 8, so is 2. So we have a degree of unsaturation of 2 for this. So, I mean, really we can rule this out because we saw a carbonyl. We know there's at least 1 unsaturation. And then this one has 1 unsaturation. This one has 2. All right, so that gives us some possibilities there. And then, and so that's what the degree of unsaturation. If we had high-res mass spec data available, we could distinguish between these molecules because we have some more exact numbers. So that's a possibility. And then we know from the functional group that we've got a carbonyl and carbon hydrogens, and that's it. So this one looks like a good possibility. If I were a betting man, I'd say that's probably our best bet because that could include a carbonyl. This one could as well, but we don't see any of the other carbon hydrogens. So I suspect it's this. So, all right. So let's look at numbers 47 and 51, and that will wrap up our chapter on infrared spectroscopy. We'll switch over to our document camera here. All right, treatment of benzaldehyde. And the structure of benzaldehyde is this. So we've got a benzene ring. So that's benzaldehyde. So we got a carbonyl. All right, when we treat it with zinc and mercury in the presence of HCl, we get another compound. Now, because I know what this particular reagent does, and this is not something that you have studied yet. I know what this reagent does, so I know what's going to happen. But not knowing what's going on here, let's see if we can figure out what's present in this particular compound based on the information that we have. All right, so let's look at the peaks that we have. We've got absorptions that go from 3150 to 2950. All right, so the 3150 to 2950 reciprocal centimeters, that tells us that we've got definitely have carbon sp2 hybridized carbon hydrogen bonds. But because it goes below that 3000 mark, it goes to the right of it, that means we probably have carbon sp3 bonded to hydrogen. So we have the carbon hydrogen stretching there. All right, 1605 and 1409. Those two peaks are, so the 1605 and 1496, that tells us that our phenyl group is still there. Not surprising. We started with a benzene ring. We're going to end up with a benzene ring. All right. You'll notice what's not here is we don't have a carbonyl. So we don't have a carbonyl. So we'll say there's no carbonyl. All right. And there's also no OH. So no alcohol present. All right. Our molecular ion is 92. So with a M over Z, that's equal to 92. All right, we'll break out our handy dandy calculator. Let's take 92 and divide by, we'll divide by 12. So 92 divided by 12 gives us 7.6. So we could have C7, and then our remainder with this, so 7 times 12 is 84. So 92 minus 84. We have 8 hydrogens. So C7H8 is a possibility. All right. Let's see. We don't have any OHs and we don't have any carbonyls. So there's reason to believe maybe the oxygen is gone. So let's look at what this structure could be. Well, one possibility is that when we treated that, we removed the carbon-oxygen double bond and put some hydrogens there. So we simply reduced it. All right, and if we look at that, it's got the carbon-hydrogen sp2, it's got carbon-hydrogen sp3, it's got the benzene ring, so it's got the phenyl group, and there's no carbonyl and no OH. So this is consistent with our structure. And so this is our probable structure. All right. Later, well, spoiler, that this is what it is. Later, when we get to the chapter on aldehydes and ketones, you'll see that this is a way to reduce aldehydes and ketones all the way down and get rid of the oxygen altogether. Kind of a cool reaction. All right. So next, treatment of anisole. OCH3 with chlorine and FeCl3 forms P, which has peaks in the mass spectrum at 142 and 144. All right. And then 129 and 127. We're going to assume that these the 142 and 144 are, we're going to assume that those are our molecular ion. And because we get that double peak, now it doesn't indicate that it's a 3-to-1 ratio, but we've got chlorine here. It looks like we put a chlorine on the molecule. All right, so let's figure out what that molecule could be. So we'll do our M over Z. It's equal to 142. And let's subtract 35 from that. And when we subtract the 35 from that, we're going to get, let's see, 107. All right, and now let's think about what that leaves for us. So 107 divided by 12. All right, it means we can have 8 carbons with some stuff left over. And that totally makes sense. So C8. All right, and we'll do, so 12 times 8 gives us 96. So let's subtract 96 from that. From 107 minus 96 gives us 11. H11. Well, not 17, H11. That doesn't seem very likely. We only had 7 carbons to start with, and we had an oxygen, and the oxygen probably isn't gone. So let's go down one more. Let's do C7. So we're going to subtract a carbon. We'll have C7, and then we're going to put an oxygen in there, and let's figure out what's left over from 107. So 107 minus the 7 carbons, so 7 times 12. All right, so that gives us 23, and then we'll subtract the 16 for the oxygen. That gives us 7 hydrogens. All right, well, that makes sense. We've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and if we took one off and put a chlorine on there, then that would be a molecule. So this is a likely structure. All right, the IR has 30, so we'll do the 3096 to 2837. That tells us that we have carbon sp2 hydrogens and carbon sp3 hydrogens. All right, because we have it on both sides of 3000. So that tells us we probably have that methyl group and the phenyl group are still present. All right, the 1582 and the 1494. Again, that's very characteristic. One near 1600, one near 1500 for a phenyl. All right, so here's what we know. There's possible structures we could have here. One possibility is that we've replaced one of the hydrogens on here with a chlorine. So for example, we could have that. We could have that chlorine. And we could have that one. The other possibility is that we replaced one of the hydrogens here with a chlorine. All right. But that's far less likely. It turns out that we're probably, if we do this experiment, we're probably going to get a mixture of this one and this one. And we will talk about why that is a little bit later. I forget which chapter it is, but it's on electrophilic aromatic substitution. I think it's chapter 16, but that's coming up soon. All right, well, that is the end of the content for Spectroscopy B. And if you look in the folder, you will see Spectroscopy C coming right up.